In this video, we're going to discuss two concepts that we've seen in the past and find some new information about them. The first concept we're going to talk about is perpendicular bisectors. And as a review, a perpendicular bisector, we start off with some segment, in this case segment AB, and we have the ray MN, such that we could say that MN, the ray MN, is a perpendicular bisector of the segment AB because MN is perpendicular to the segment AB and the distance from M to A and the distance from M to B is the same. Now, since we know we have a perpendicular bisector, we can pick a point, any point, on that perpendicular bisector, this ray MN, and we will find that that point X will be equidistant to the endpoints A and B. So if we look at that as a picture, we've got this segment and its perpendicular bisector. We pick a random place to put our point X, and we can compare the distance from A to X and the distance from B to X, and we will find it's the same. And if we take the same situation but place the X at a different location on the perpendicular bisector, and once again compare the distance from A to X and B to X, we will find that those distances will be equal. If we take the situation and once again place our X somewhere else, again comparing A to X and B to X, it will be the same. And once again we can see that we can pick a point X on this perpendicular bisector, and the distance from A to X and the distance from B to X will be the same. This is known as the perpendicular bisector theorem. In our textbook it states that if a point is on the perpendicular bisector of a segment, so when we pick that point X and put it on the perpendicular bisector, then it is equidistant from the endpoints of the segment. Additionally, if there is some point equidistant to the endpoints of a segment, and what I'm saying there is I have some random segment, PQ in this case, and a point R such that R is equidistant to both P and Q. So P to R is equal to the same as Q to R. Then we know that that point, in this case the point R, is on the perpendicular bisector of the segment. So if we draw this perpendicular bisector, and we can see that this ray MR is perpendicular to the segment PQ, and the distance from M to P and the distance from M to Q, making it bisecting the segment PQ. So we can see that the segment MR is the perpendicular bisector. Looking at this, which looks, it's an acute isosceles triangle, almost looks like it's equilateral there, but it's an acute isosceles triangle, and here's definitely an obtuse isosceles triangle and another acute isosceles triangle, where we have the vertex angle in each case. We've got this vertex angle, or this right here, and so we're looking at that random point. We will note that in each case that point is on the perpendicular bisector of each of those bases, or those segments that we would have started off with. This is known as the converse of the perpendicular bisector theorem. And in our textbook it states that if a point is equidistant from the endpoints of a segment, then it must be on the perpendicular bisector of the segment. Let's look at the next concept, which is angle bisector, and to brief review of what an angle bisector is. An angle bisector can be a line or a ray that cuts an angle into two congruent angles, or meaning two angles of equal measure. So if we take an angle, in this case angle ABC, and we put in the ray BK such that we have two congruent angles, or two angles of equal measure, we say that BK, the ray BK, is an angle bisector because those angles that it's been cut into are equal in measure. Now what can we do with this concept that we've already had? And we're going to talk about some point being on the angle bisector. And we find that any point on the angle bisector is equidistant to the sides of the angle. Well, what do we mean by a point being equidistant to the sides? We're talking about the perpendicular distance. Whenever we want the distance from a point to a line or a segment, we want the perpendicular distance. So let's look at the situation. We've got the angle ABC, and we have the angle bisector BK, and we have a random point X, and when we take these perpendicular distances here, we have this perpendicular distance right there, and we compare both of those perpendicular distances, we see that they are equal. And so here's a different point X on an angle bisector, and it is also equidistant to the sides of the angle. And here's a third angle with some random green point, and that green point, when we look at its perpendicular distances to the sides, they are the same. This is known as the angle bisector theorem. And in our textbook we read that if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. Additionally, we find out that if there is a point interior to an angle that is equidistant to the sides of the angle, that's confusing just in that. So let's look at the picture of that. We have an angle PQR, and we have some point T, and it says so I have a point that's interior, okay, but it has to be equidistant to the sides of the angles, meaning that this distance from T to M, this perpendicular distance, and the distance from T to N, the perpendiculars, are the same. So now I have this situation. If there is a point, in this case T, interior to an angle that is equidistant to the sides of the angles, what do I know about that point T? Well, what I know is that T must be on the angle bisector of the angle PQR. And let's look at a couple different situations. Here's an angle with this point that's interior to the angle. Here's another angle with a point interior to it. And here's a third angle with a point interior to it. And what we will note is that in the first angle, that point happens to be equidistant to the two sides of the angle. And the second angle, that point is equidistant to the sides of the angle. And in the third situation, that point is equidistant to the sides of the angle. So in all three cases, I know that the point that I have that's interior to each one of those angles must be on the angle bisector of each one of those angles. This is known as the converse of the angle bisector theorem. And in our textbook, it reads, if a point is in the interior of an angle and is equidistant from the sides of the angle, then the point is on the bisector of the angle. Those are your 4 new laws that are building on 2 concepts that we have known for a while.